Okay, all right, let's get started. So today we'll finish solar. We'll finish solar, and then we'll continue on to wind energy. So as a reminder, right? So midterm is next Monday. This will cover up to solar energy. So we'll cover up to the end of solar power. So I will release a homework with solutions will be posted tonight, right? So the solar questions will definitely be on the midterm, right? So since it doesn't make sense to have a homework together with a midterm, then I will post a homework with solutions. So think of these as exercise questions. But then definitely you expect to know the materials that will be covering this homework. Any questions about this?
So the homework solution for homework 4 is going to be posted today also?
No, it's due tomorrow, right? So I'll post that after the due date.
Oh, okay.
Yeah.
Thank you.
Okay, so the midterm will cover to, we'll finish solar sometime this lecture. We'll cover up to there. Okay, all right. So this is the mid, right? So this is so today our plan is we'll do solar, and then when we finish solar, we'll go into wind power generation. Okay, so these are the two big renewable generations we'll cover. Then continuing from last time, where we covered to was, as a reminder, our circuit was this type of circuit. Right, so we have a solar cell is really a current source in parallel with a diode. And then based on this voltage as the load, we can control the current drawn by the load. Right, so the current really is IS minus the current through the diode, which is IS minus I0, T minus 1. So this is our voltage and current relationship, where the solar current is given by nature, and the voltage on the load, you can think of something we get to control. So this is our fundamental equation for the solar cell circuit. Then of course, you can look at how this varies with the effect of irradiance rho. So what this means, this is the solar power density. Right, so this just says if you get more solar irradiation, what happened to the curve? So let's say this is our VI curve. And then so that if you look at this voltage, if you look at the current as a function of voltage, we get something, something like this. So then what happens if you get more irradiation? What happens if your solar density goes up? You get more sunlight. How does this curve change?
Does it just get shifted up?
Right, this whole thing got shifted up, right? Because really how the solar irradiance comes into this solar current, right? So this depends on the solar power density. So as we get more irradiance, more sunlight, then this whole thing just shifts up. Right? So this shift goes up by a constant. So this is rho 2, rho 1. Okay. So again, the impact of sunlight comes into this current source. Right? So we'll never calculate, we'll very rarely calculate what this IS is. Right? But sort of keep in mind which of these numbers depend on the irradiance value. So if you look at the impact on power, it's the same thing, right? So normally if you plot the V versus power curve, then the curve goes something like this. So you have more sunlight, then the curve goes up. Right? So it shifts the entire power curve up. And then the point of maximum power will change. Right? So this is Vmax 1, Vmax 2. Okay? So you, based on what the irradiance is, to generate the maximum amount of power, you actually have to change the voltage. Okay, so at each time, right, at every time instant, there's a feedback loop inside your solar cell that determines what basically the solar current is, trying to measure the current coming out of the cell, and then try to adjust the voltage, let's say to maximum the power consumption. Okay, so there's a fair bit of electronics around the solar cell that continues to adjust the voltage drop, adjust the voltage according to how much current the cell is generating. So it's not you put a cell here, you connect two wires, there's a load, and you generate power this way. You have to do some control on the voltage, on the output voltage of the cell. Any questions about this?
Question. So, is this the same as the power of gradient that's make the thing shifted?
Sorry, can you repeat the question?
So, like in the last graph, it shifted up, right?
Yeah.
And then this is the same effects as the radiant effects, right?
This is the same effect, although the impact of this is that the maximum power point changes. Right?
Oh, so that's why the graph is like kind of curved.
Right. So you curve, right? So it's a nonlinear relationship. So this is basically just shift up by a constant, right? So the current goes up by a constant. But then the maximum power tracking point is voltage times current. So it's not a simple relationship. The curve will shift to the right and go up. So you need to change your voltage set point if you want to extract the maximum power.
Okay, thank you.
Right. Okay, so temperature, again, we can look at the impact on temperature. There's again, depending on where the load is, you may be sensitive to temperature impacts. So often you actually try to sort of, depend on which temperature you're operating on. Sometimes you try to cool the panel, although it's much rare for solar. So most often what we care about is based on the different amount of sunlight, the maximum power tracking point changes. So we want to follow the maximum power tracking point. So nowadays, if you buy a solar panel, you can think of you're buying both the panel itself, like the material, and the control and electronics around it. Nowadays, the cost is actually half-half. So about 50% of the cost is everything around the panel, about 50% is the material cost. So if you look at the cost of solar, if we want that to keep going down, then what really we need to do is to both have cheaper panels, right? Make cheaper panels, as well as make cheaper electronics and control circuitry around the panel. Okay, so often when you think about improving solar panels, you think of material science. If you want to change from silicon, some other material, how do you do that? But whatever material you use, there's actually a stage afterwards that tracks, for example, the maximum power, that has a good feedback control, things like that. this equally as important as having a good material. You can have a perfect material, but if your electronics around it is not very good, you still don't extract all that much power. Okay, so this goes hand in hand. You look at a lot of inverter company or company that's selling you solar. A lot of innovation is actually coming from, how do I, track this maximum power, right? How do I deal with this? Right? How do I quickly track it? How do I, reduce a loss, for example, in my circuit? So these are as important as, at least from our perspective, as how you make the panel themselves. Okay, so that's something to keep in mind when people talk about the cost going down. It's both the cost of the material and the cost of the, for example, the some DC to DC converter going down. Okay? So we need both. We need both to happen. All right. So then, of course, as we said before, you can connect panels in modules, right? So you can connect things in series. Then what happens when you connect things in series is you add, right? So the current needs to be equal, right? So the current needs to be equal. So they have S1, S2. You have two diodes. Things are in series. And then you have a load. So the voltage goes up. So the voltage, when you connect things in series, the current doesn't go up, the voltage goes up. So basically, you're connecting two current sources, right, in parallel, in series to each other. So the current must be the same. Then if you connect things in parallel, then of course the current adds, but the voltage stays constant. So here, if you want to increase the current, you get a combined current source with larger current, but then the voltage stays as before. Any questions about series and parallel connections? Okay, so if, from a circuit's perspective, this makes sense. Can you think of some challenges when you have a module? Let's say if you put this module on your rooftop, can you think of some challenges that may happen when you connect many, let's say, current sources together? So space is one, right? So you always need enough space. But other than space, let's say, some real-time concerns. When you're operating the module, do you see some challenges that you have to think about? Right, so Wenxuan, right? So if one of them breaks, the whole thing doesn't work, right? This is like a serious connection. If one panel has a fault, then the whole thing goes on. There's another thing that happens more often before, other than kind of failures. So think about it, if you have this sort of a module on your roof, what could happen if you have, a reasonably large roof and sort of a whole panel over it? So what happens when a cloud goes over your house, right? So what happens in practice, often you have partial shading. So what this assumes, let's look at series connection if you want, as I get the same solar, right? I got the same solar current. But then of course, if you have partial shading, right? Part of the panel, part of the module is, covered by cloud or a tree, something, shadow of a tree. Part of it is not. Then they're not equal, right? One has, naturally, fundamentally more current than the other. But then the question is, what do you do when this happens? Right? Then often you're limited by the least amount of current you can pull, right? So you have 10 in series. One of them gets covered by a cloud, or the sunlight comes from another direction, you're covered by shadow. Then you lose current in this entire series branch, right? So that's a loss efficiency. So this is some, this is a very practical problem we have actually. So often partial shading is really a problem on your roofs. Right? Right? So especially for a place like Seattle, when the angle of the sun changes quite dramatically, between different seasons, right? So there are some sort of fancy things you can do in the circuit to make the situation better, right? So again, this is outside scope of this class. We're going to assume that things are perfect. That have some current source in series, they all generate exact same current. But knowing that in practice, when you design a module, again, there's a lot of electronics goes in that try to make sure, right? What happens if you have shading? What happens if you have, one panel gets dirty, another one's relatively clean? What happens to all this imbalancing? There's a lot of balancing you have to do. We will connect current sources together. It's not as simple as the way we drew here. Just put them in series, then it's okay, right? Okay, any questions about that? Just something to keep in mind. When you see a solar panel again on the rooftop, it's not, there's some electrical engineering goes beyond. Right? It's much more beyond just, again, panel, wires, load, and you're done. Right? There's, because of different situations we could have throughout the day and year, there's many things you have to think of when you design this type of circuits. All right, so this, but for us, we're going to most times think of ideal situations, right? So everything's the same.
I have a question. So can you go back to the last slide?
Mm-hmm.
It's like I try to follow the lines of the diodes 1 and 2. It doesn't seem in series somehow. It looked like in parallel to me. Can you kind of draw?
This is series. This is how the current will flow.
Oh, okay. And then that second current source is attached it to the load, and then it's go into a cycle. That's why.
Right. So the current source comes out this way and flows this way and goes into the other current source.
Okay. Thank you.
Yeah. So this is in series. Just follow the line. Yeah. Okay. Any other questions about this? Okay, good. All right, so this is how you stack them together. So let's do one example. Right, so let's say I stack 50 solar cells in series, right? So I really want the high voltage. So I'm going to stack all of them together at 20 degrees. The solar current in each cell is 1 amp, and the reverse saturation is 10 nanoamps, right? So we want to understand the voltage and power diagram. Right? So again, this is trying to show that basically the current stays the same, right? The current stays the same, but the voltage gets boosted by quite a bit. You boost the voltage by a lot. So you look at this question, then again, we can do the per cell computation. Again, in this question, we're going to assume that each of the cells sees exactly the same temperature, right? They all see 20 degrees, even though you have 50 of them. So in this case, we compute the thermal voltage. Millivolts. Then the current, right? The diode current is I0 e to the VVT minus 1. So this V is basically, you can think of, this is let's say this is the current going through each of the cells, right? So then if you look at the total module voltage, then this is 50 times the voltage across each cell. Okay. So the current doesn't really change once you chain all the cells together, but the voltage goes up. So what happens to this curve is, if you look at the V plot, then it pushes the power plot, it pushes the curve very much to the right. Okay, so you can have a very high voltage. Okay, you can operate this at a much higher voltage when you connect things in series, right? Because each of the cells only sees 1/50th of the voltage. So a series connection boosts the voltage, and if you have a load that operates at say 20 volts, then it's better for the load to connect things in series and just boost the voltage that way. But then of course you have to make sure that in practice, not all of them will see 20 degrees Celsius temperature, right? Each cell will see a slightly different temperature at least. Then so you have to worry about how do you balance the current? How do you make sure that you're drawing the same amount of current out of each cell? Okay, so this is, again, we actually design this. There are some feedback mechanisms that make sure the currents are correct in this situation.
So I know you said it's outside the scope of this class, but in practice, just high level, does it kind of average it out? Like if you've got one end of your module at 30 degrees and another end at 10 degrees, does it kind of just average them out to 20, or is that not how it works?
Yeah, that's not how it works. So the problem with series connection is you're often limited by the current, by the cell with the least amount of solar current. Right, just the way the current sources work. So it's not as simple as averaging it out. You're closer sometimes to the least efficient one, or the one that's generating the least current. Because you don't really want to charge your solar cell, right? If you're drawing more current than the solar current is providing, you're basically trying to charge your solar cell. And that's not a good idea.
Question.
Yeah.
So for the draw graph IV, it said to draw IV and IP. And then I don't know what equation for, like, how do you get like that graph to be that exact,
Oh, you just plot this, right? So we have a PV equation, right? So last class we had this equation. Right, so what would happen to our PV equation? This, right? So just plot this equation.
Oh, okay.
Yeah. So we will look something like that. So peak, somewhere. Yeah, so it's a fairly simple equation to use. So yeah, so you can draw it and peak somewhere. So when people install panels on roofs, and often there's actually a lot of work to make sure you install them in the right place on the roof. Right? You're facing the right direction, depending on which way your house, how exactly the orientation of your house. There's some work on where to place the panels, and it's not you towards the amount of panels on your roof gets you towards the power. There are some good places to place them. There are some not so good places to place them. So there's a lot of practical consideration that comes in here. Okay, so this is how the cell works. Of course, up to now we've been covering this ideal cells, right? So of course you lose, right? You don't capture everything. There are losses in the cells, right? So not all the photons coming to the cell. You don't convert all that energy to electric energy. And also in the circuits, we'll always have some loss elements when we have a circuit. Right? So if you look at losses in the PV cell, it normally breaks up into two categories: irradiance losses and electrical losses. So irradiance losses really comes from two aspects. One is actually just reflection. Right? So the top of your PV cell will reflect some light. So you lose some light. They never make it actually to the material. They never strike electron. They just reflect it. So that's one part of loss. Again, the second one, as we said before, is light has a very wide spectrum, wide range of energy levels. And we only capture the ones that have the right amount of energy, right? So some don't have enough energy to excite electrons. So it doesn't matter at what intensity, they won't generate current. Some have too much energy and convert more to heat rather than current. So we need to capture sort of the right energy photons that again is material dependent. So what do you think the percentage of loss is? So how much, let's say you have a photon that arrives with 1 unit of energy. How much of it is lost through these two mechanisms?
About 70%.
Yeah, 70%, right? So this is 70% of this goes away, right? So we're now very 70% of, right? So the reflection part you can try to help, but then the more fundamental part is you want material that capture a wider spectrum of energies, right? You want them to generate current over a wider spectrum of photons. And that's really a sort of the sort of state of our research is how do I make better materials. So that's state of our research there. For us, as when we design the panel, we're given a panel, so so it's we already lose 70%, but then this is really sort of the loss and not something you can deal with circuits. This is more towards the material part. Right? So the loss with respect to circuits, this is more familiar to us. This is the resistance, basically, in the wires. Okay? So these losses are just resistances. So you have resistance in the wire, you have resistance in the material. In the semiconductor, right? The semiconductor has some resistance. So together of these will also, in addition, give us some loss, right? That's converting to heat. So if you look at the real model for PV, then there's two sources of resistance we can add. One is this thing in series with the solar cell, and this is really just resistance of wires. And this just models the fact that I have a wire, it's not a perfect conductor, so I add RS to it. Then there's another resistance in parallel, which this is some internal resistance of the cell. This models the fact that I have a semiconductor crystal. Right? So you lose some power when the current goes through this semiconductor. Okay? So this is a more practical model of the solar cell.
Is the semiconductor the one with the RS?
No, RS is the wire. Sort of the fact that you're putting a wire into this cell. Right? So that's in series. The RP is the internal resistance of the semiconductor.
Oh, okay.
Yes. Any other questions about this model? So this type of modeling is quite common. Normally, when you go from ideal circuit, to a more practical circuit, very often you have some component in series. That's typically, in our case, model some resistance of the wiring. You have another component that's in parallel that's have something to do with the internal structure of the device. So we'll see this type of circuit again when we look at, for example, transformers, or look at induction motors. This is quite common way of coming up with ideal model and adding this non-ideal components to the model. Okay. Right. So again, we can, right? So the circuit is again not all that much harder to work with, right? It's just instead of one diode, you have a diode in parallel with a resistor. So the equation got slightly more complicated, but not all that much more complicated. All right, so there are often sort of two efficiency factors now we want to talk about, right? One is, so because we have two sources of loss, one efficiency factor is you have power coming in, how much power is converted to electricity. Right? This is the irradiance loss we talked about. Right? Some of the power doesn't make to a current. So how much of power gets converted to electricity? Then this electrical efficiency is how much power gets to the output of the cell. How much power is lost in the internal structure. So these are the two efficiency factors we want to talk about. Right? So it turns out the solar cell, the overall efficiency is not terribly high. It's around 20-some%. No, mainly because their irradiance efficiency is quite low. And most of the light, or majority of the light, we don't convert it to electricity. Right, so we can do an example to see what some of these numbers look like. Right, so let's say I have a solar cell with some area. So I have solar cell with this area operating at 30 degrees Celsius. I have output current, I have a low voltage, and I know the reverse saturation current of the diode. Okay, I have some resistance of the cells, then I have some solar power density. So I want to calculate, given this is my solar power density, how much power do I get at the end of the day? Right? Exactly how much power do I extract from this? Okay. Given the fact that I have all these losses. Okay, so our goal is to say I have a circuit that looks like this, compute how much power gets to the load, compare that with the solar power density of 200 watts per meter square. Okay, so we want to see how much of this 200 watts per meter square make it to power the load. Okay, so the calculation is again, goes along similar lines, right? We want to compute what the voltage, the thermal voltage is, we want to compute what's the voltage over the load, and we want to compute what are the currents going through this circuit. Okay, so again, we compute the thermal voltage. Again, the important thing to remember, this is in kelvins. Okay, so let's remember this is in kelvins, not in degrees Celsius. So this is our VT. We can also compute this voltage across the load. Because in this problem, we're told what the current is, right? We're told what its current is. So then what is, right? So we want to now compute VD. Okay. So we know V is 0.4 volts. We know the voltage across the load. We know I, the current, is 1 amp. Now, how do I compute VD? How do I compute the voltage across the diode? If I know what the low voltage is and I know what the current is.
See how much voltage drops across the series resistance if you're given that?
Right, so we know the series resistance, right? We know this is 10 milliohms. So we know VD is V plus current times RS. So 0.4 plus 1 times 0.01. This is our voltage drop across series resistance is 0.41 volts. Okay. So now I can compute the current across ID, right? Because the reason I want to compute this is I want to know what the solar current is. That will tell me how much power I'm actually pulling out of this. How much power I'm pulling out of this current source, right? To compute that, I need to know what ID is. I need to know how much current going through the diode. To compute how much current goes through the diode, I need to know the voltage across the diode. Okay. So here I have current as reverse saturation current, VD over VT minus 1. This is 6.64 milliamps. Okay, any questions for this?
Can you go back to the problem?
Okay.
Okay, so the I0 is 1 nanoamps.
Yeah, 1 nanoamps. Yeah. So this is given. Yeah. 1 nanoamp.
Okay, thank you.
Okay, so now I know ID, right? So I still need to compute IP, right? Because my current source gets divided into 3 currents. The current goes through the diode, going through the shunt resistance, and the current goes through the load. So my current now goes into the shunt resistance, this RP, this is VD over RP. Right, so this point for 1, we know what the shunt resistance is. This is 1 kilo ohm. Yeah, 1 kilo ohms. So this is relatively small, right? This is 0.41 milliamps. So my total current coming out of the current source is the sum of all these. This is 1.00705 amps. So so the efficiency I get, this irradiance, eta irradiance, this is the voltage I have across the source. This is also VD. Times the solar current, this is the amount of power I'm pulling out of the current source, divided by my solar power density times how big my solar cell is. This is my irradiance efficiency. So this is 0.41 times, this IS from above, 200 watts per meter squared times 0.01 meters squared. So I get about 0.025 or 20.5% efficiency. Right? So I extract about 20% of the energy that's contained in the sunlight gets converted to electric power.
So
any questions for this? Yeah, go ahead.
So the units of the area you want it to be in meters squared.
Right, so you need to be consistent, right? So this solar cell is given by 100 centimeters squared, but the density is 200 watt per meter squared. So we need to make the unit line up. So you can either convert the density to per centimeter squared or convert the area to per meter squared.
Okay, yeah. I see.
Right, so the units are always chosen to be most natural, right? So if you have a small panel, it doesn't make sense to talk about in meter squared. But then, to talk about solar density, you want to talk about meter squared because that gives us reasonable size numbers. Okay, so pay attention to the units, especially for a question like this, right? We have centimeter squared, meter squared, milliohms, and kilo ohms. Right, so all of these are of different units. Right, we have a nanoamp, for example, in reverse saturation current. So you need to make sure you convert them to the right unit when you do the question. So just a bunch of units floating around. Okay. So this is the irradiance efficiency. Now, of course, we also lose some power, right, in the 2 resistors. But it turns out in the resistors, we don't lose all that much power because the electric power loss, this is I squared RS loss plus IP squared times RP loss. These are typically pretty small compared to other powers we have, right? So the electric efficiency is pretty good. This is power out over the power input, but this is the power input minus the power loss input. So this, so you can compute this way. So this is 0.975. So the electric efficiency is pretty high. Right? So the total efficiency, even though it's a product of the 2, is pretty much dominated by this. This dominates. This efficiency dominates. So to make a more efficient solar cell, really what you need is you need a better material. Right? You need to absorb more of the sunlight. Whereas the electrical connection become interesting if once you start making modules and panels. You connect many of them together, it becomes more interesting how you control the circuit. Any questions about this?
So what is that symbol called? Like the name of it?
This is eta, Greek symbol eta. This is very, so E is for efficiency, right? So it's Greek symbol for efficiency.
So this is the efficiency of the irradiant, right?
So do you have the product is the total efficiency, right? It's made of two parts. The efficiency you lost because you don't convert all the solar energy to electricity. And then the efficiency you have because some of electricity is lost in the circuit.
And what does that stand for? Like the name of it for that, like full name?
Just overall efficiency.
Eta.
Overall efficiency.
Okay.
Yeah. Any other questions about this?
Yeah, I had a question.
Yeah, go ahead.
Could you explain how you found VD once again?
Oh, okay. So, right. Okay. So, where's VD? Right. So VD, right? So we know V, right?
Yeah.
So we know VD minus V over RS equals to the current.
I see.
Right. So then we know the current, we know V, we know RS. So we just got VD that way.
Okay, got it. Thank you.
Any other questions?
Can you go back down? More down.
Okay.
So the total efficiency of that is gonna be like the products of those two, like that.
Right. Yeah.
Okay.
Yeah. So it's always efficiency is a product, right? You lose, this X% from this effect, you lose another Y% from another effect. So 20% efficiency is not bad for a solar cell. 20%.
I thought in my head like they have to add up together somehow.
No. You don't add efficiency. It's always efficiency is some number between 0 and 1, right? So you have to multiply them. All these are some number between 0 and 1. You multiply them together, it's still a number between 0 and 1, right? So this is what efficiency. So again, if we on the midterm, if you calculate efficiency, it's not a number between 0 and 1, right? Then it's definitely not correct. Right, so that's a sanity check. Also on the midterm, you'll see some circuits, right? Don't panic. The circuits we have in this class again can be solved pretty easily using basic circuit theory, Ohm's laws and things like that. Okay, all right. So this is the sort of technical equation part, right? This is the equation part. So if you look at assessment of solar PV cells, of course, the cost keeps on going down. This is the sort of reverse Moore's law effect, right? The costs keep halving every decade or so, or every 20 years. And right now it's a little bit stabilized because again, we're hitting a point where the electronics start to matter, not just the material itself. So now it's to continue reducing the cost. It's really a matter of doing both. Making better, cheaper materials and making better electronics, making better controllers to extract more power. When, for example, you have shaded solar panels that has partial shading. So all these are starting to become more important. Whereas let's say going between 1970 to 1990 is really, can you make it cheaper? Can you just make a cheaper panel? Nowadays is, can you make a more sophisticated panel? Can you add functionality around it? Can you add control around it to make it more efficient? And so we're at that point of the scaling now. All right, so many solar panels are actually used quite often, right? So we look at calculators, watches, we use it all over the place. In space applications, it's really easy to build solar panels. Right? There's no shades, so you can turn towards the sun and things like that. So that's very often used. But in other applications, we're transitioning towards more solar. But again, it's still a little bit of case-by-case basis of exactly, do you recover the cost or do you make money back? Right? So it's still case-by-case basis. But really, what solar panel has the potential to do, because actually, if you look at a place that does not have a reliable electrical infrastructure, building solar panels is probably one of the best thing you can do, or one of the easiest and cheapest things you can do. Right? So this picture is trying to be a little bit cute in this case. But still, the message is if you don't have access to wires, if there's no power line running to you, then your best bet nowadays is actually just build a solar system. And this is actually, there's a lot of hope that as we get the cost down, as we understand storage and solar together better. Whereas before, when you try to electrify a remote area, it costs a lot of money. You have to build a long transmission line. Right? It's a long line, costs a lot of money. You have to figure out how do you buy the right of way for transmission line. All that is complicated. But then if you can build this or standalone solar system, we are getting good at building that. That has a lot of potential for areas that does not have existing infrastructure. So that's the, so the push in solar actually is two parts. One is you're in a city like Seattle, how to integrate more solar for a system that is not designed to handle solar. Another is if you go to a very remote area, how do you build a solar system for a place that has a very weak connection to the rest of the bulk grid? We do see that actually in the US, for example, state of Washington has places like that. It has both sort of places. So it's again, an interesting research area for solar. Any questions for solar?
It's like, I was thinking that Seattle's have rain for 10 months, a year. And then would it still be worth it to use solar panels?
Yeah, it's still worth it. Depending on the application. So in Seattle, you cannot build a standalone solar generation. Right? Unlike say Phoenix, Arizona, where you can pretty much go to solar for a lot of places. Seattle solar cannot be the dominant generating technology. But still solar can give you quite a bit, right, on the margin. So solar will help. Even during winter months, solar, shaving off the peak helps. Because nowadays, most utilities are not limited by the energy consumption through the year. Most places are limited by the peak power consumption. So if solar can come in and shave off 10% of the peak, that can reduce your cost by 50%. Right? It's very, very, the cost is scales very non-linearly with the peak. Right? For example, I think this week's homework, there's a question saying, right, so, we said, oh, we have one generator that turns on 2 weeks of a year. Look at the cost of that generator. Right? Look at how much it costs for that generator to break even. If I can replace that by solar and storage, then that makes a lot of sense, even in a place like Seattle. So it's misleading and not really correct to think of the total energy output of something, or at least that's not the entire picture. Nowadays, it's really, really important to think of how do I deal with the peak? It's almost never the total energy that bothers us. It's almost always the peak. We cannot supply the peak power. We worry about the peak. We don't worry about the throughput, the total throughput of the year. Any other questions? Yeah. Any other questions? Okay, so good. So our midterm will cover up to here. Sorry, so this is midterm up to here. Okay, so let's take our break. Come back at 3:32. We'll start with wind energy. Talk about wind energy. Yeah.
So for the midterm, do you also like, is it gonna come up with like problems or like questions or like general things about like the advantage of this, the advantage of that?
Mostly homework style questions. I don't anticipate there will be sort of short answer type of questions. Most will be, get a number, right? So the solution of most problem will be a number.
Okay.
And please circle your number. So circle your solution. All right. So the number one problem with grading this kind of exam is I can't find where the solution is. All right. So please circle your solution on the midterm.
I have some problems with problem number 4 on the homework.
Okay, all right, yeah, so let's break now if you don't have a question about homework. So we'll come back and 3:32 to continue with wind energy, right? So let's look at homework. Question, which one? All right, okay, so let's get started again. Right, so we finished with solar, we'll go to wind energy, which is actually quite different than solar, right? So it's a switch, we'll go from thinking about semiconductors and photons to more classical mechanics for solar energy. So if we look at solar energy, then, we look at wind energy. Then wind energy is really a very old technology in some sense. We used to have wind turbines generating electricity for a very long time, right? But then our in more modern times, we really have a lot of growth in wind, right? So have quite a bit of growth in wind. Wind is probably sort of the largest form of renewable power if you don't count hydro in the United States or around the world. Okay? So the goal in this class is look at basically how much energy you can extract from wind, right? How do you extract energy from wind? And so we'll look at some aerodynamics. We'll look at what is the efficiency you can possibly get. How does wind energy scale with wind speed and the size of the blade and things like that. Okay, so our goal is to understand if you have a moving mass of air, right, how much power do you get out of it? And then how much of this do you actually can you convert into electrical power? Okay, so that's our goal for wind energy. And so when you extract energy from wind, really, we're looking at you have some kinetic energy in your moving mass of air. So for kinetic energy, as a reminder, we have 1/2 m squared, where we use m as the mass, w as the speed. We use w for speed is because we want to talk about wind speed. Right? So v is, we use w. It's more common to use w for wind speed instead of v. Okay. So, but anyways, the equation is, is a simple equation, it's just 1/2 mv squared. Then we want to think of, out of this kinetic energy, how much of it can we capture? Right? So the way we capture this energy is really, wind has some energy coming in, as moving body of air, will pass through some cross section. Right? Think of the turbine, rotating turbine as some cross section area. Wind will pass through this cross sectional area. The question is, how much power can I get out of it, right? Or how much energy can I get out of it? Okay. So if you look at the energy equation, we have kinetic energy is 1/2 m w squared. W is the speed. This is in some sense, right? We can measure wind speed pretty easily, but the mass is hard to talk about, right? So it's hard to think of mass. We don't really think of, the mass of the moving air. Right? So how do I relate this mass to something like cross-sectional area A? Right? So we build a turbine, we know what the cross-sectional area is, we know how fast the wind is moving. We don't really necessarily know what the mass is, or we don't really think of things in terms of mass. So how do I relate this? How do I relate M to something like A? Any ideas?
Well, you've got the air density, so I'm guessing that as well.
Right, so how do they relate together then? How does the cross-sectional relate to air density, relate to time?
I think there's a volume.
There is a volume, right? So there is a volume.
Oh, you look at how much, depending on the speed and the time, then you'll see how much has gone through the area, and then you can multiply by the density.
Right. So that's right. So those are correct, right? So mass is really volume times density, right? So we know density, right? We can measure density pretty easily. Then how do I convert volume? Well, volume is just the area, right? My cross-section area times how fast wind is moving times the time wind moves, right? So this is my volume. So times the density, this gives me mass, right? So I'm looking at the volume, how much volume passed through this cross-sectional area. This is just the size of the area multiplied by how fast it's moving, multiplied by how long I'm looking at, multiplied by time. Okay, so this is my equation, relating mass to density, cross-sectional area, speed, and time. So we don't need to talk about mass. We can think in terms of speed and area. Then if you look at the kinetic energy of air, right? So we start with this equation. We don't want to work with this equation, or it's not a very insightful equation. So it's easier to think of mass as volume times density. This is area times speed times time times square of speed. So kinetic energy is really 1/2 area times density times time times cube of speed. Times cube speed. So how do you convert energy to power? So this is energy. How do I think of power? How do I convert energy to power? Right, divide by time, right? So we want to get rid of this time variable, ready? Right, so again, we design wind turbine. We know area, we know density, we know speed. So we want to get rid of time. So we divide by time to get the power density again. Right? So the wind power is a kinetic energy divided by time. So per unit time, how much we get. So this is 1/2 A delta cube of W, so speed cubed. So the density is the wind power divided by the area, how large the area is. This is 1/2 delta cubed, right? 1/2 delta speed cubed. Okay. So this is, for example, in units of watts. This is in watts per meter square. So this is our equation. So the important to note is everything is proportional to this thing cubed. This is the important relation to know. The cubic of power basically depends on the cube of the speed. Okay. So this scaling tells us the speed of wind is really, really important to how much power we can generate. Right? So if you want to build a wind turbine anywhere, then really you want to target places with high speed of wind because this cubic relationship. Right? This goes up in cubic. So if you look at the plot, right, since it's a cubic relationship, this goes up very sharply. It goes up very sharply, right? And really is what you have is, right? So if you increase the speed, if you double speed, power goes up by a factor of 8, right? So this goes up by a lot. So if you think about it, if I have 1 hour of a 20 miles per hour wind has the same energy as 8 hours of 10 miles per hour wind. So if you think from an energy perspective, the sort of power density perspective, then really speed is much more important than, say, if you have a steady stream of wind or not. Right? You really care about what is a fast speed of wind you can capture. Right? So if you go to a place, you can double the speed. You only need to operate 1/8 of the time to recover the same amount of energy. Right? So this cubic relationship is important. That's why people build turbines at some very not so convenient locations, because if I can squeeze a little bit more speed out of this thing, then it's really worth my while to look at power. Right? That really worth my while in terms of power. Okay. Any question about this? Right. So again, cubic is a very fast growth, right? So this cubed is really sort of what makes, say, where to locate wind turbines, speed becoming very important for wind turbines. Whereas you don't have this kind of scaling for solar. Okay, for example, if you look at, again, say, Seattle and Southern California, the irradiance differ by a lot, right? But the power doesn't differ by an order of magnitude. Whereas if you look at a place with very calm wind versus a place with a lot of wind, with a very fast speed, then the power can differ by orders of magnitude. Right? So it's really, wind is a lot more sensitive in some sense to where you place it compared to solar, because there's cubic relationship on speed. So solar, for example, the dependence on irradiance is not this large. You don't have this type of dependence on irradiance. Whereas when you have this kind of dependence on speed, it's cubic dependence on speed. Okay. All right, so that's why we build wind turbines at inconvenient places, because you really get much more bang for the buck at those places. But density also enters into the picture. But then density really doesn't vary all that much. So if you look at this equation, as you go higher up, the density reduces, but it doesn't drop that quickly. Doesn't really drop very quickly. So often we'll use 1 kilogram per meter cubed for density. Very often we'll just use this number, and this is a pretty good approximation for density of air. Questions for this? Okay, so then the next dependence is on the area, right? Power is also proportional to area. Area is proportional to the square of blade length. Right? So this tells us you really want to build the wind turbine to be big. Okay? We want to build big wind turbines because big wind turbines really is, if you double the blade length, you can quadruple the power you capture, right? So high speed is the most important thing. And second is you want to be able to build big wind turbines. And those two factors really matters to the amount of power you can capture. Okay, so this is the basic equation for wind, right? So this is all the power that contained in a moving body of wind. So of course we don't get all of this power out, right? We don't capture 100% of the power. So the way we capture this power and the way we're gonna turn this sort of power in the moving air mass into electrical power is through a wind turbine design, right? Through a blade on the turbine rotating. So if we want to look at the blade's aerodynamics, then a wind turbine blades is very similar to aircraft wind. It operates with almost exact same principles. As if you look at the turbine blades, it has an airfoil shape. And then you try to generate lift on this airfoil. You try to turn the wind turbine because you're generating some lift on the airfoil. And by turning the wind turbine, this will turn a generator, and that will generate electricity for us. So if you look at the principles of aerodynamics of this, right? So we all heard the story, right? You have some air coming into the wind turbine, right? So you have some air hitting this leading edge, then air separates into two paths, separating two components, and then one moves along the upper chamber, one moves along the lower chamber. Then the air molecule, right? So then the story is the air molecule separates and they meet at the end of the day and they meet at the trailing edge. Right? So then for the people who's familiar with the story, then what's the implication here? If the air separates and meets at the end, right? So what does this matter if I have an air and it separates at the two upper edge and the upper chamber, lower chamber?
The air on the lower chamber goes faster than the air on the upper chamber.
Air on the upper chamber goes faster than air on the lower chamber, right? So you have a longer distance on the upper chamber because of the shape, right? So we have the speed is on the upper chamber is faster than the speed on the lower chamber because air has to travel a farther distance. They have to meet at the end. So one is faster than the others. Then you talk about Bernoulli's principle to say, okay, you generate a pressure difference because the speed of the air. Then that pressure difference causes lift, right? So this is the standard theory of how you generate lift through Bernoulli's principle. And then this is also the theory presented in the reference book, for example. Right? So looking at this, so the short story of this theory is not correct. Well, this theory has not much to do with why lift is generated. It doesn't mean there's no pressure difference, but the story of a changing speed causing a pressure difference, thus generating lift, doesn't have much to do with why airplanes fly or why does wind turbine turn and generate power. Okay, so if you look at this story, can you identify something wrong with the story? There are some simple thought experiments that we can easily come up with to basically saying this theory is a bit bogus of how lift is generated. Can you think of some experiments that would create some issues for this theory? Right, so let's generate some thought experiments, right? So if this theory is correct, right, and the speed on each edge matters, and then that creates a pressure difference. So if you take an airplane, can airplane fly inverted? So if I turn an airplane around, does the airplane fly? For example, if I turn this airplane upside down and try to fly airplane, can I still fly the airplane? Does it still fly?
Yes.
Yes, right. Airplane, you may not be very comfortable in the airplane, but the plane flies fine, right? But if this theory is correct, then the plane cannot fly because there's no lift. You're being pushed down, right? That doesn't work. So if you think of a paper airplane, also paper airplane flies fine. It doesn't directly go to the ground, right? It glides in air, creates some lift, can go up and down. But if you look at a paper airplane, then the edge is completely flat, right? There's no speed difference on a paper airplane, lower, between the two edges. Right? So paper airplane also flies. But if this theory is correct, if this is how lift is generated, then again, a paper airplane shouldn't fly. Right? It should drop like a rock directly, when you release it, go to ground. Right? So this theory is not really how airplanes work or how airfoils work. This is also a reason why we don't use a textbook, right? This is also a reason why we don't use a textbook, because it's just not why airfoil would turn, right? This is not why airfoil why turbine turns is not why airplane flies. Has some effect, right? Doesn't mean it has zero effect, but it's not the reason why lift is generated. Right? So again, as we said, if you look at the theory, and again, this theory is incorrect because planes fly inverted. There's no, again, it's not very efficient. Planes can fly inverted. It's fine. It's not efficient, it's not comfortable, but they do this. Paper airplane flies. Right? Paper airplane flies. Wings are completely flat. There's no airfoil shape to the wings. They fly. Right? And another thing is, right, this question of, how, right, why would the air molecules meet at the trailing edge, right? There's no, it's a molecule. Why does it know how to meet at the trailing edge? Okay, so this is not really why. So the theory of pressure difference, speed leads to pressure difference, leads to lift, doesn't explain all these phenomena. So can you think of a reason why airplanes fly or why does turbine turn? There's a different principle other than Bernoulli's principle that governs how lift is generated. Can you think of any? Any suggestions of why airplanes fly? Or how do you generate lift? Tilt the wings, right? So that's almost there. That's almost there, right? So wind transfer the flies because you tilt the wings, almost. So which law of physics do we use? There's a very simple law that we all know that actually governs how planes fly. Any guesses which law of physics we use?
Newton's theories.
Newton's third law, right? So Newton's third law. Planes fly because Newton's third law, right? Planes fly because we're pushing the air downwards. And then we have to go up. Right? You're pushing air down, you have to go up. And the reason you can push air downwards is one, because you have an angle of attack, right? You're tilting the wings. Second is because the airfoil shape actually works because the air is sort of a viscous fluid. So it hugs the shape of the wing. Because hug the shape of the wing, the air gets bent downwards. You're bending air downwards. Because you're bending air downwards, something has to push up, right? So that create an equal opposite force pushing up. So the airplane, that's the way lift is generated. Because Newton's third law, action of Newton's third law on air. It's really not a pressure difference per se. Right? So there's some pressure difference, but that's very small compared to the action coming from Newton's third law. Right? So again, plane can fly if you don't have an airfoil shape. Right? As long as you push the air down, you will go up. Right? But then the airfoil shape helps you because the air wraps around the foil, and that helps to bend air down more. That helps you generate more lift or become more efficient at generating lift. So that's the high level reason of why air works, right? So air goes down, airfoil goes up. This is just Newton's third law for us. Any questions about this?
Yeah, so it looks like in the tip of the front of the airfoil, air is being pushed up, but is it because even at the top, halfway into the end of the airfoil, the air is bending down? Is there just more net bend down than that little bend up right by upwash?
Yeah, so the overall the air is going down. Yeah, so on average air is going down.
Okay, thanks.
Yeah. So there's a sort of common misconception. A lot of times we learn Bernoulli's principle, but really it's not why things work, right? So that's a reason why we don't want to use a textbook. It's hard, right? So textbook actually gives the reference book. We don't want to use a reference as textbook. It gives Bernoulli's principle, but it's actually more of just Newton's third law, right? And that what makes our airfield design complicated is because you have to understand this aerodynamics and what happens when you change speed, and how does air exactly flow along the wings, all that you need to take into account. So the design, the exact shape design is complicated, but the overall principle is Newton's third law.
So is the same true for cars? Like obviously a race car at high speeds can generate lift and come off the track. Is it because they're pushing air downwards as well down the backside of the car?
Yeah, you're pushing air downwards or backside of the car, right? So you have this air that gets bent downwards. So that's why you have the cars will modify the tail, right? To not push the air down, to sort of make it disperse more. So this is the main mechanism of generating lift. Bernoulli's principle is it's hard to get much lift out that way. It's really not easy to get lift out that way. Okay, so this is the principle of generating lift. So makes sense to stop here today. Next class, we'll look at things like how do you control how much lift you get. Right, so basically the way to control the lift, how much lift you get, is how much you tilt the airfoil, or for wind turbine, how much, what's the pitch of the blade. So next time we'll look at that, angle attack and pitch, and understand for wind turbine, how do you relay the power you generate to the pitch, right? So for a solar cell, the power you generate is related to the voltage of the load. Here for a wind turbine, it's related to how you pitch the blade. Right? So we'll stop here today. Next class, we'll go into a lot more detail about pitching the blade and how do you control power generation. Okay. So a good reminder, midterm is next Monday. Homework will be released today with solutions. So that's an exercise question on solar. And midterm will cover up to solar. All right, okay, thanks guys. So next Monday, the class is basically an office hour to answer any questions you may have for the midterm. All right, thanks guys.
Professor.
Thank you.
Thanks.
Thank you.